Okay, so thank you very much. So the title of my presentation is Effect of Moisture and Temperature on the Deformation of Unsymmetric Laminates, and is the basis for applications of 4D printing of composites. So myself and my master student, Alfred Raju, we come from the Concordia Center for Composites at the Department of Mechanical, Industrial, and Aerospace Engineering at Concordia, University of Montreal, Canada. So basically what I want to tell you is we want to see the effect of moisture and temperature on laminates that are made using the technique of 4D printing. And the main advantage of this technique is that we can make the complex shapes using only a flat mold. I think my presentation may be a bit different from other kind of presentation in the sense that the materials that I use are not similar to what you use. What I use here is mainly the composite material. These are made of carbon epoxy, long continuous fibers, and they have high stiffness and high strength. Now, to say this, that there's nothing wrong with this, the fact that you have using soft materials, because I think you have applications for the soft materials. But the reason I do this because my background is mainly on composite materials. I work for many years on the long continuous fiber composite materials. So basically, what I show is that this is the material that I use. In the sense that you take a look into normally the pre-pregs. We call the pre-pregs, I mean the pre-impregnated, the fiber is made of carbon, and the matrix is epoxy. And they come in the form of a sheet. And the sheet, the thickness of a sheet, like a thickness of a sheet of paper. And it is sticky on both sides, okay? And in the sense that is very stiff and strong along the fiber direction, but not so much transfer to the fiber direction. So on the right-hand side, I show a schematic representation of one particular layer, called one particular sheet. And you can see that the blue lines represent the fibers, and also the white region represent the epoxy matrix. So that means these fibers are embedded inside the epoxy matrix. So basically, that is the material that I use, which is quite different from the case that you have, okay? And basically to compare between what I call the regular 4D printing and the 4D printing of composites. Regular 4D printing, these are the kind of things that I have seen in papers from other people, in the sense that usually they use soft plastic. And if you want to increase the strength and stiffness, you add soft fibers into it. Whereas the material that I use here, we use the polymer matrix composite with long continuous fibers. In terms of the stiffness and strength here, normally you have, for the case of 4D printing, the stiffness is about maybe 1 gigapascal to 3 gigapascal, and strength about 10 megapascal. But for the 4D printing of composite, we talked about 155 GPa, and the strength maybe about 1,500 MPa. And so, in terms of the way how you can make the structure change the shape, for the case of regular 4D printing, usually you vary the material within the XY plane. So that way, then when you subject it to some kind of a heat or moisture absorption, then I think the different kind of properties at different point make it to change the shape. Whereas the case of 4D printed or composite, the material is the same within the XY plane. We don't change that within the XY plane, except that we change the fiber orientation from layer to layer. That means along the Z direction, along the thickness direction, we change the fiber orientation from layer to layer. So this case here, the case of regular 4D printing, the change of the shape depends on the variation of material within the XY plane. Whereas for our case, it changed from layer to layer. And I could say that in the case of regular 4D printing, I think you have the material is more or less isotropic. Whereas here, we talked about anisotropic, and we depend on the anisotropy as a way how to change the shape. So this case here, that means in the sense that we depend a lot on the layup sequence. We talk about layup sequence. For example, you have one layer at 0, one layer at 90, another layer at 45, minus 45, and so on. So usually this kind of people working in a composite, they use mostly symmetric laminate. Symmetric, that means that the orientation across the midplane is the same. Whereas in the case of 4D printing or composite, we use unsymmetric laminates. Unsymmetric laminate, I mean you have a laminate here, say 0 degree, 90 degree. And so we depend on this anisotropy to make the change of the shape. Because, for example, in this situation along the 0 degree orientation, the shrinkage is less. Whereas along the 90 degree orientation, the shrinkage is more. So basically, that is the kind of principle of operation. So in the case, I want to show you the operation. The machine that we use, we call an automated fiber placement machine, which is a very large machine compared to the 3D printer. But it works, it is the additive manufacturing in the sense that it deal with the deposition of layers. So I want to show you a quick video to show that. So you can see that you have strips of the material that are fed into the roller. And then in this case here, you can either apply some kind of heat to melt it to make the salt, and you can put the layer to stick together each other. And you can use the robot to vary the orientation of the fibers from layer to layer if you wish to. So I wish to say that this is a large machine, it's a small scale. And companies like Bombardier or Airbus or Boeing, they use huge machines to make the aircraft structures and a similar kind of principle of operation. So I just want to give you a very quick example of what we have made using this kind of technique of 4D printing. And I give 5 different examples: the SPCs, the composite flowers, composite leaf spring, the stiffeners, and also the flexible core, corrugated core for flexible aircraft wing. So I have presented some of these before, so I'll go over that very quickly. So that means in the sense you want to make a shape like this, like an S shape. And we want to do this without a complex mold. We only use a flat mold. So that when we do that, then you put the first layer at level 1, 0 degree here, 90 degree here, and level 2, 0 here, 90 here. So basically across any particular location of the laminate, you have an unsymmetric laminate. So by the time you cure and cool it, the flat shape changes into this shape. And then another kind of a shape we made, we call the composite flower. You can see that in this case, we make a flower that consists of 4 petals, and each petal has 5 leaves. Each of the leaves here has different curvature. So that means that you can see that if you use a regular method to composite manufacturing, you cannot make this because you cannot make a mold with 5 different curvatures. So this kind of a structure can only be made using the technique of 4D printing or composite. And again, I just want to repeat, we only lay down on a flat mold. We did not need a complex mold to do this, a flat mold, and at the end result, we have this shape. Another thing that we have done before is a composite leaf spring. This way here we use a 60 layer, 36 layer of 90, 24 layer of 0. And we make this kind of a shape, and then we subject to the stiffness constant of 486 Newton per centimeter, which is equivalent to most of the relevant engineering stiff spring available. And we subject it to fatigue testing more than 1 million cycles from our curve to our flat shape and without failure. Another thing that we have also made is we call the omega stiffener. This kind of stiffener here. Normally in aircraft structure, people use some kind of stiffener to kind of stiffen the wing skin. And the stiffener can be at the shape of an L shape, C shape, Z shape, D shape, I shape, J shape, or the omega shape. So that's what we did in terms of this case. We make this kind of omega shape for the stiffening of the skin structure. And also early this year, we also published a paper talking about the flexible wing. This case is a portion of a wing, of a flexible wing. And we use the technique of 4D printing to make this kind of a shape that we call the corrugation. You can see you make the corrugation with a lot of curvature like this without the need to make a complex mold. We only use a flat mold to do this. So these are a few examples that we have made in terms of structures. So the main topic of the discussion today is that people are asking the question, suppose we are subjecting to this unsymmetric laminate. So what is the effect of moisture? I mean, the moisture in the air, and also the temperature operation on the shape. Does it change a lot or not? What will be the situation? So for practical application, we need to answer that kind of question. So that is the subject of my topic today. So first, the effect of moisture on the radius of curvature. So this, in order to measure the effect of the moisture or the radius, we need to find a way how to measure the radius of curvature. So there are 2 different kind of techniques to measure the radius of curvature of a piece. One is called the perpendicular chord method, which is a very old method. If you can get the piece on your hand, you can trace the shape of the curvature on a piece of paper, then you can draw the perpendicular bisector. You can draw a bisector number 1, bisector number 2, you get the center line, and from there you get the radius. So this is a very simple technique. If you cannot really get a hold of your piece, suppose that you put the piece inside the oven when it's hot, and you need to measure the curvature during the hot condition, then you cannot trace that on a piece of paper. So here we use image analysis using a program called DigiMiser. Basically, in this case, this one take a picture of the shape, and then they trace the curvature, and then we put in some kind of a scale here, and the program get the dimension from the scale, and from there it can provide to you the radius curvature. So again, using a software program, fairly simple kind of thing to do. So what we did is that in terms of trying to study the effect of moisture onto the change of the curvature, so we make laminate, we make sample. Here we make 0-90. Again, this has only 2 layers, mainly for experimental study. So it's fairly thin. So the length is 300 millimeter, the width 150 millimeter, and we follow the curing cycle. This is a curing cycle to really subject to this kind of material. So you have a piece like that. And then from there, we expose to the environmental condition. We leave that inside the room condition, and the temperature was about 72 degrees Fahrenheit, and the humidity was about 30%. So we leave it there for 7 weeks, and then we monitor the shape, the radius of the sample as a function of time. So this curve here shows you the moisture content as a function of time. So we weigh the sample at different interval of time, and we plot that against the square root of time. So here the moisture content versus square root of time. And we have these other points, and then we fit them with the Fick's law. You get the Fick's equation, and from there you get the line here. So it seemed to be well behaved in terms of the absorption of moisture. And then from there we also measure the radius of the sample as a function of time. So you can see that the radius increase at the beginning. At the time that we go from about 7 centimeter to about 8 after about 150 hours. So that means roughly about 150 hours is about 5 days. Then after that, stabilize in terms of the radius. And then also after that, we take a look into the effective curve of temperature. If you heat it up within a certain range, what would be the change of the curvature of the piece? So here, what we do is that we put that inside an oven, and then again, we vary the temperature of the oven at different temperature, and also we measure the radius as a function of the temperature. So here we have 110 degrees, 140 degrees, 160 degrees, and so on. So from there, you obtain the average radius as a function of temperature. You can see that we start from room temperature, and the lines seem to be fairly linear up to about 90 degrees centigrade. And beyond 90, that it pick up fairly quickly. So I would say that within the range, maybe in the operating temperature, into the sense that if the piece is operating within room temperature up to 90 degrees centigrade, and you have a fairly small amount of increase of the radius, and it's fairly linear from that point of view. And then also here we also do the calculation using laminate theory. Using laminate theory to calculate the radius of curvature as a function of temperature, and compare that against the experiment. And it seemed to be agreeing fairly well in the sense that they go from this kind of a range. So from this case here, that means that it looks like there is a good amount. There is a change, maybe about 30% change in the radial curvature during this range. But this is for the case where you have a very thin laminate, only 2 layers, 0-90. And for practical kind of structure, normally the laminate is thicker. And so we would like to see in the case of practical applications where the effect of the temperature and the moisture is significant or not. So we take a look into the effect of the thickness on the change of the curvature. So what happens is you take a look into the equation for the curvature as a function of, these are A1, A2, A3, these are laminate stiffness. It's a function of the lab sequence, how many layers you have, the material, and so on. And these, the MXT, NXT, these are the thermal stress resultant and the moment resultant. And these are function of the change in temperature and so on. So this case here that we put in the relation between these stiffness constant and also the stress resultants, and we find that the K sub X is equal to 1 over PH. Now P here, that is the number of the layers. Suppose you have a laminate sequence of 0P, 90P, how many layers 0, how many layers of 90, then P is that number. And H here is the thickness of a layer. So that means in this sense here, it looks to me like the radius curvature is inversely proportional to the thickness, because the thicker the sample, the higher the value of P. So that means that we have a thicker laminate, you have a smaller radius curvature. And then also the effect of thickness due to the moisture and also the temperature. So if you take a look into Fick's law shows that the amount of moisture absorption is proportional to the maximum amount. And also here you have the main important thing here is the time. T is the time and H is the thickness. And you can see that the amount of absorption depends inversely proportional to thickness and proportion to the square root of the time. So that means in that sense, if you have a thickness of an laminate that is 2 times as thick, then it would take 4 times more in terms of the moisture to come in. So that means for thicker laminate, the effective moisture is less because it takes a long time for the moisture to get in, because of the fact you have a thick one. So I mean, during whatever the time of operation, so the moisture may not be that significant in terms of the effect onto the behavior of the shape. And also in the sense that you have a thicker laminate, you have that will be more difficult to make, So that way, then the study that we made is only on a very thin laminate of only 2 layers, but for thicker one, the effect will be less. So for conclusion, we can say that the moisture absorption has a slight effect, and in the temperature range from 20 to 80 degrees centigrade also has slight effect. And like I say, the information can be useful for the design and operation of the structures made for the printing of composite. So I would like to thank the Natural Sciences and Engineering Council of Canada for the financial support, and I thank you for your attention.